Hey, happy Friday, everyone. Welcome to the very first Howlin at the Moon Science Friday. As I mentioned in my email a few days ago when I teased and promoted this, there is a long-running series on National Public Radio called Science Friday. It's been on for, a generation. I listened to it way back in the 90s. And like a lot of things in not only in public radio, but in the mainstream media in general, I think it used to be a really good show. They had a lot of great guests. They talked about science at a level that I found to be informative without being condescending. But all of that has kind of gone away over the last, 10 or 15 years. And like a lot of things in the media, particularly in national public radio, there's a huge amount of liberal bias. And when it's not liberal bias, it's bias towards, frankly, stupidity. You know, they have Bigfoot people on there. They have all kinds of crazy people on there that are not scientists, that are not functioning in any way, shape, form, manner, or style as an actual impartial investigator into the wonderful mysteries of the universe. The universe surrounds us with things that we don't yet understand. And as a scientist, it was my great privilege for a generation to be able to go to work every day, and my job was to be able to try to crack some of those mysteries and then communicate that to my students, the things that we had found out. So what I want to do with this series is every Friday just spend a few minutes, not a long time, 5, 10, 15 minutes maybe, talking about something that I think will be recognizable to you instantly, and just try to break it down so that you understand the world around you a little bit better. And I'll promise you two things. One, it won't be a waste of your time. You'll know more than you did by the time you're finished. And second of all, I'll try to keep it entertaining in addition to being informative. So it'll be fun and edifying. I guess those are my two promises. And I won't tell you anything that I don't think is true. So as I said in the initial promotion, I'm going to start out by talking about the atmosphere. And I think that's a topic that I'm going to stick with the first few of these Science Friday shows. On planet Earth, we actually have two oceans that we deal with. We live at the top of one and at the bottom of the other. The boundary between the two is actually where we exist. The first ocean, and the one that you would think of, which covers, more than 2/3 of this planet, is the ocean that consists of water. This is a water planet with a little bit of dry land, but it's mostly ocean. We live at the top of that, but then we live at the bottom of another ocean, which is an ocean of air. And both water and air, by the way, are considered fluids in physics. So we live at the boundary between those two oceans. And we may talk about the water ocean a little bit later on, but for now I want to talk about the ocean of air that's above us. And the atmosphere is not homogeneous entirely throughout. It changes as you go higher up, vertically higher. For one thing, there's something called a lapse rate, which means the temperature in general decreases about 5.5 degrees Fahrenheit per 1,000 feet. So it gets cooler as you go higher in the normal course of events. Now, that's not always true. There are things called inversions where the atmosphere actually gets warmer as you go higher. But that's something that happens relatively close to the ground in the layer of atmosphere known as the troposphere, the layer that's closest to us. Above that, there is a stratosphere, then there's a mesosphere, then there's a thermosphere. We're not going to differentiate those today. We're just going to talk about the atmosphere as a whole. And the atmosphere is almost entirely composed of nitrogen and oxygen. It's about 78% nitrogen. Almost all the rest of it is oxygen, along with some noble gases, some water vapors, some particulates, and that's about it. But if you look at just nitrogen and oxygen, that is 99% of the atmosphere you're talking about right there, more than that. And the interesting thing about it is that most of that consists of molecular nitrogen and molecular oxygen, N2 and O2. They're called diatoms. And the interesting thing about these diatoms, they're very, very small, is the way they affect the light that comes into the atmosphere from the sun. Now, the sun produces a broad spectrum of light. It appears to us to be kind of yellow because we're looking at it through the Earth's atmosphere, which screens some of the light out and tinges it a little bit. But the sun, for all intents and purposes, produces white light, with a little bit of a peak in the middle of the spectrum. So if you were to go into space, it would look mostly white with just a slightly yellowish tint to it. It's a fairly common type of a star. So that light, which is mostly white with a little bit more intensity in the center of the spectrum towards the yellow, around 550 nanometers, enters the top of the Earth's atmosphere. Now, there's some terms that we need to go through first to define for the purposes of this discussion, so you'll understand what I'm talking about. And the first of those terms is something called refraction. Refraction is what happens when you take white light and you pass it through a material denser than the vacuum of space. And when you do that, that white light slows down. Light travels at one speed in free space. It travels at slower speeds in all denser media. And the amount by which it slows down depends upon the density of the medium and also the wavelength of light. So white light is composed of all the colors of the rainbow combined together with roughly equal intensity. When that white light enters a denser medium, like our atmosphere from space, it starts to refract or separate. And the blue wavelengths slow down at a different rate of speed than the red wavelengths or the yellow wavelengths or the green wavelengths. That's how you produce a rainbow. That's how a prism produces a rainbow. You take white light, send it into the prism, and it separates it out into its constituent colors. Well, when light enters the top of the Earth's atmosphere, there's a certain amount of that takes place, but there's another thing that competes with that, and it's called scattering. And scattering is what happens when you take light, typically white light, you put it through a denser medium, and that light kind of gets scattered around. The directions change. And in terms of the Earth's atmosphere, the N2 and the O2 diatoms, which again are more than 99% of the atmosphere, will take that white light, and most of it just passes straight through. It doesn't affect most of the component colors, the reds, the yellows, the greens, things like that. Doesn't affect them. They just continue to go straight through. But it really likes the blue light. And so what the N2 and the O2 diatoms in Earth's atmosphere do is they pick off, so to speak, that blue light, and they start to just scatter it around. It's like a ball inside of a pinball machine or something. That blue light just gets scattered all over the place. So what happens in that particular case is that when you're standing on the ground and you're looking up in the air, you see blue light coming at you from all directions because the N2 and the O2 diatoms in the atmosphere, again, they take that light and it's like a ping pong ball in a machine. It's going all over the place. So everywhere you look, you're going to see blue light coming from your direction, and that's the reason why the sky is blue. Now you might say, well, wait a minute. If N2 and O2 diatoms preferentially scatter blue light, it's called Rayleigh scattering, which is true. Why isn't the sky purple or violet? Because that's even a shorter wavelength. And that's an excellent question. And the answer to that is there's actually two answers, one that's simple and one that's a little more complex. The more complex one is something called optical depth, and I think we'll just pass on that. You can look it up if you want. But the simpler explanation, which is most of it, is that your eye is much more sensitive to blue than it is to violet. Once you start getting close to ultraviolet, the sensitivity of your eye tapers off a little bit. It's not linear across the entire spectrum of colors that you can see. So since it's not as sensitive to things like violet, and it's not at all sensitive to ultraviolet, you don't see those colors as intensely. You're going to see the blue more intensely, and that's most of it. All right, well, so far so good. So that explains the color of the sky, the blue, most of the time, but the sky is not always blue, is it? Sometimes it's white, sometimes it's gray. At sunrise and sunset, the sky is typically orange or red. So let's talk about that a little bit. And sunrise and sunset differ. The geometry is basically the same, but they differ a little bit from the amount of particulate atmosphere that tends to be in the sky at a given location. At night, particulate matter tends to drift down out of the sky because human activities go into sort of a lull. Everybody goes to sleep. During the day, human activities pick up. That stirs up some dust and other particulates, PM10, PM20, things like that. They go into the sky. Cars run around, soot, things like that. Those all get thrown up into the sky during the day. So sunsets are a little bit different than sunrise just because of the amount of particulate matter. So that's why sunsets typically appear a little bit more reddish than sunrises do. When you're talking about sunrise and sunset, and let's just restrict ourselves to sunset right now, understanding that sunrise is the same thing, it's just not as intense because of the lack of particulates. What happens then is that the sunlight is coming in at a lower angle, and two things happen when the sunlight comes in at a lower angle. The first is that it comes through a much more thicker section of atmosphere at a lower angle than it does as coming straight down through. Think of the atmosphere as like a thin blanket that surrounds the Earth. The shortest way through that blanket would be straight through it. If you come in at an angle like that, you're going through a much thicker cross-section of atmosphere. And two things happen when you do that. First of all, the scattering, after a while, a lot of that light is going to be scattered off in directions that you can't see anymore. And second of all, there's going to be some absorption that goes along with that. So what happens is that the shorter wavelength stuff gets both absorbed and scattered off in directions that you can't see. Well, if you take white light and you subtract away all of the short wavelength stuff, you're left with yellows and reds, and that's why the sky appears to be somewhere between, a dark yellow and orange or red around sunset. When there's a lot of particulate matter in it, which screens out almost all of the short wavelength stuff, then it's going to appear to be a really deep red. That's why when you have volcanoes or forest fires or things like that, you get these really blood red skies, particularly at sunset. So that explains why the sky is blue in the middle of the day on most clear days. It explains why it's red and orange at sunrise and sunset. But what about on days when it's gray or white? And what about clouds? Clouds are white. What causes that? Well, that's another phenomenon. Rayleigh scattering, that selective scattering, is what explains the blueness. What explains white is something called Mie scattering, M-I-E. Mie scattering occurs when white light is scattered off larger things than N2 and O2 diatoms. Those are very, very tiny. Typical Mie scatterers in the atmosphere are water vapor and water droplets, which are much, much, much bigger, orders of magnitude bigger than N2 and O2 diatoms. So instead of just selectively scattering the short wavelengths, Mie scattering centers scatter everything. Well, since the light coming in from the sun is predominantly white, it's going to scatter everything. So when you look at a cloud, you're looking at a gigantic Mie scattering center. So you have sunlight that enters that cloud. It's full of water droplets, cloud droplets, and they just scatter white everywhere. So every place you see that cloud, you're seeing water droplets that are scattering white light or cloud droplets that are scattering white light. Now, sometimes the base of the cloud is a darker color than the rest of the cloud. Clouds are typically white, kind of a silvery white, but sometimes when you go down to the bottom, the cloud gets darker and darker. That's because there's liquid water down at the bottom of the cloud, and the liquid water tends to absorb the light, so it just gets darker. It kind of just subtracts it right out of the spectrum. And in fact, very experienced observers can tell you the water versus snow and ice content of a cloud just by looking at it, because the color of the cloud is kind of a giveaway to how much liquid water is in the cloud. So there you go. Examples of a blue sky, an orange and a red sky, and white in the sky. And there's one more thing we could talk about when it comes to white and Mie scattering, and that is fog. So when you're in a fog bank, you're in a cloud, basically. For all intents and purposes, you're in a low-lying cloud. And everywhere you look around you, if it's in the middle of the day, it appears to be kind of white. And the other thing you might have noticed is when you're in a cloud, your eyes will hurt. If you're not wearing sunglasses, your eyes will hurt a lot. It's a lot like being on snow in the winter sometimes. If you're not wearing your goggles, or if you're driving on a concrete freeway instead of an asphalt freeway, the light can be blinding sometimes. That's because when you're inside a fog and there's sun directly above you, if it's a thin layer of fog and there's some sun above you, which is typical, the white light from the sun enters that fog and it gets scattered in all directions. So if there is no fog, if you look away from the sun, you're lowering the intensity of light and the amount of light that enters your eye. But when you're in the fog and that white light is coming at you from all directions, there's not really a direction that you can look where you're not getting a lot of light coming into your eyes, and it hurts your eyes. Same thing when you're driving on a concrete freeway. That concrete on a sunny day reflects a lot of light. Snow is that way. Snow reflects better than 95% of the sunlight that hits it. By the way, when we're talking about reflection, reflection and scattering are not the same thing. They both change the direction of light, but they do it in different ways. Scattering is random. So when white light hits a scattering center like an O2 diatom, it can be scattered in any direction, okay? But when something is reflected, there's some geometry that goes along with that. There's two types of reflection. There's spectral reflection and there's diffuse reflection. Spectral reflection is what all of you are used to in terms of reflection. It's the type of reflection that you get from a mirror. So when you look in a mirror, there's some strict geometric rules that are obeyed by the light that hits the mirror and the light that comes back off of the mirror. And we won't go into what all that is. You know intuitively what it means. Diffuse reflection is something a little bit different. Diffuse reflection is what snow does. I told you earlier that snow reflects better than 95% of the light that hits it. But you can't see your reflection in the snow because each of those little snow crystals, even though it's obeying the geometric law of reflection, they're all sitting at slightly different angles, so you don't get a composite reflective image like you do out of a mirror, which is flat. So each of those little crystals is obeying the law of reflection as it should, but you can't compose an image because they don't all come to a point where you can form an image plane in your eye, so to speak. So it's a little bit different. That's an example of diffuse reflection, but it's still reflection. So refraction, scattering, reflection are things that affect the way the atmosphere looks. And we're going to get into this a little bit more later. Well, that's all I have for you today. I just wanted to get into today why the sky is blue. When I was teaching, every once in a while I would be on some graduate student's committee. And that was always the question I asked, why is the sky blue? Rarely, in 25 years of asking that question, did I get an entirely correct answer. I got, well, the oceans are blue and it's a reflection from the ocean. I got all kinds of crazy stuff. But now you know the answer to the question that a lot of physics graduate students couldn't answer. All right, BC. Cheers.